Welcome to our talk on the UCL findings paper, Multiplication, Multimodal LLMs. So let's begin. When an LLM sees 47 times 36, hears 47 times 36, or reads that equation inside an image, we want the same thing, the exact product. This project asks a simple question: does the modality or problem surface form change the computation? The answer is yes, but in some subtle ways. Modality can shape how what we'll call arithmetic load impacts performance and internal model routing. And here's why that matters.
Modern agents will inspect screenshots, slides, scans, voice traces. In all these settings, the arithmetic errors aren't cosmetic. A wrong product can become a wrong invoice, a wrong ledger entry, an inaccurate downstream decision. The key point here is that difficulty is not just about digit length. Sparse 5-digit operands like 40,000 times 30,000 are structurally easier than dense 5-digit operands like 45,327 times 36,215. Therefore, the benchmarks that we're going to build in this project must hold the arithmetic load fixed while changing only the surface form and only the modality in these investigations for how models are performing arithmetic across these different modalities.
Our benchmark starts from a generator. It creates one multiplication problem, then renders that same problem as numeric text, as an image, and when possible, as audio. That gives us around 10,000 shared instances with one answer key. The comparison here becomes clean. Did the model fail because it could not read the input or because it could not compute the product? Without this pairing, modality effects get mixed with problem differences. Now we need one scale for arithmetic difficulty.
We will here, therefore, define arithmetic load, C, we'll call it, as simply as total digits times non-zero digits. For example, for 47 times 36, there are 4 digits total and 4 non-zero digits, so C equals 16. This C metric is not perfect. It ignores some carries and shortcuts, but it captures broadly how many digit multiplications the model has to carry in its internal algorithm computing these problems. Notice the contrast at the bottom of the slide. We have here 999 times 888 and 900 times 800. These look similar in size, but the load to compute these problems differ sharply and alters the computational burden. C characterizes that burden. So with C defined, we're now going to share some of our first results.
Here's the first set of empirical results. Across 6 model families and variants, the probability of a correct answer falls as C increases. The curves differ, but the performance cliff is consistent. Gemini 2.5 Flash, QN30B, GPT 4.0 cross 50% accuracy around where C equals 50 to 54. QN 235 holds until roughly where C equals 74 to 75. GPT 5.4 and Grok look stronger in numeric settings, but become more fragile under alphabetic images. So load is not the only thing, but it is the dominant axis. And next, we'll watch how the input channel shifts the cliff.
Numerical images here often track numerical text closely. A picture of the problem compared to the text tokenization of the problem yields similar C performance. Here, QN235B, for example, C will equal around 275 in text and 75 in numerical images, the 50%. Alphabetical images do expose a different sort of weakness. For example, GPT 5.4 drops by about 8 C points from numeric to alphabetic images. In other words, images of the problem compared to images of the problem in number form versus in alphabetic form written out fully. Grok 4.420 drops about 19 C points in the same setting. The takeaway here is that the same arithmetic can fail either when the model must translate a surface form into a different calculation route or when the overall C burden becomes too great. This raises some objections. Maybe the model here is just misreading the input across modalities, and that's what's changing some of these modality differences.
Our perception robustness tests help answer that objection. So on match perception tasks, models are above 99% in accuracy, so they can read or perceive the numbers, but the failure would then seem to appear later. The bottleneck is the arithmetic process after perception. And from there, now we ask how the model tries to compute the arithmetic with different heuristics.
The paper will compare three heuristics for performing arithmetic. OT here will denote columnar schoolbook route or style arithmetic. DD will denote decomposition, where we decompose operands into place value chunks. RC will denote the approach whereby we round to nearest bases and then compensate for that rounding. Instead of trusting self-reports here of the model, we're going to score short heuristic-specific continuations under forced completions. A lower loss here will mean that the model finds that continuation more natural in that problem context. This is going to ask what computation style does the model's distribution or does the model's internal routing seem to prefer? And the answer is actually surprisingly consistent.
Across QN30B and QN235B and across text and image, decomposition has the lowest forced completion loss. So for QN30B text, DD beats the neutral baseline by about 0.506 loss points. In image, DD is still the least costly heuristic. And for 235B, the heuristic prompts sit above neutral, but DD remains the lowest loss. So the model's default approach is not columnar multiplication. It leans toward decomposition, and the natural intervention is to steer that heuristic choice, and the result is cautionary.
Here, to perform this heuristic steering, we train LoRA adapters for OT, DD, and RC traces. The hope here is that by steering the model towards the right trace, we might be able to improve the arithmetic, improve performance. But we find that it does not. The adapters here change behavior, but almost always hurting correctness. So the lesson here is not that strategies don't matter, it's that the model's base router seems to actually perform better than any single imposed heuristic.
The LoRA updates for OT, DD, and RC move in nearly orthogonal directions. The cross-heuristic cosine similarities are small, about 0.07 to 0.12 for 30B and about 0.03 to 0.06 for 235B. And same heuristic reruns are more similar than the cross-heuristic pairs. So strategy separation looks robust here. Forcing one route disrupts the learned router.
In terms of takeaways, here are a couple things to remember. First, digit structure predicts failure much better than modality alone, although modality also matters. Perception is also solid in these models. Models can read these problems effectively. However, they can still produce inaccurate results even after reading the problem correctly. Third, strategy priors are also measurable here. We can use these forced completion probes to learn about which of the different algorithmic approaches tends to be dominant internally. Fourth, we find that imposing rigid traces on the model's internal reasoning is also dangerous. This can make arithmetic worse. For more information, please see neurastemic.ai.